nevertheless, behind Professor Salim's picture is I think it's the Senam, right? It's the location of the Conservatoire National Arts des Métiers.
Yeah, which is here. The inside is.
Yeah, it's in the center of Paris.
Yeah.
And and today, Prof. Salim, he has also interest in optoelectronic physics, and in particular infrared radio frequency, infrared detection of optics and physics. And also his interest is in microelectronics, in particular radio physics also. And he has many publications in numerous scientific journals. And you are also the editor of a journal, right? I think from the MDPI journal.
Yeah. Electronics.
Okay. Yeah. So the journal is about what is the name of the journal?
The topic is about optical amplifier, which is different topic than the one I will speak today. This is the new trends on microwave amplifiers or power amplifiers for next generation of communication.
Okay, so you are also the I think the head editor of this the joint editor of this journal.
I'm co-editor of this special topic on this power amplifiers for next generation of communication systems.
Okay, so maybe I can introduce you also in a little bit in bahasa.
Yes.
Prof. Salim Faci adalah associate professor di Senam di Paris, di Perancis, dan beliau visiting scientist professor di IPB University for 3 weeks, selama 3 minggu, 2 weeks in Bogor and 1 week in Jakarta. So Prof. Salim juga meneliti tentang fisika kuantum mechanics, terutama terkait topik hari ini adalah quantum cascade laser ya. Jadi teman-teman mahasiswa, salah satu kendala di dalam radio elektronik saat ini adalah untuk dapat menghasilkan frekuensi komunikasi di infrared ya, daerah mid infrared, di mana untuk itu diperlukan inovasi, di antaranya adalah menggunakan quantum cascade laser. So one of the important application of quantum cascade laser is that you can produce radiation in the mid infrared region, and Prof. Salim will also talk about this ya. Jadi dengan menggunakan persamaan kuantum nantinya akan dihasilkan suatu aplikasi untuk mid infrared laser, mid infrared radio frequency, di mana pentingnya itu adalah salah satunya adalah komunikasi yang lebih cepat ya, with faster ability for communication at high frequency. Oke, baiklah, kita tidak akan berlama-lama. Prof. Salim, please, the time is yours to present your topic for today.
Okay.
Yeah, maybe you can try to share the screen to test whether it is. Yes, very good.
Which one I did? Is it okay?
Yeah, I see the first screen. Yeah, with your picture. Yes. Okay.
So I have.
Yes, you have like 1 hour less for this. Yeah, just around. Okay.
Including question or.
Let's yes, you can also you have extra question 20 minutes.
Okay. Thank you, Dr. Handradi, for this introduction. So thanks, thank you all for being here. It's my pleasure to present today this talk. So it's my first time here in Indonesia, and so I'm happy to be here. So I was 1 hour before in Bogor. So I gave this talk online. So hope that next time would be in presence. Yeah, I'm associate professor from l'ECNAM, Conservatoire National des Arts et Métiers, which is a high-level institution of education in France. And I'm working in laboratory. I just here put the laser. And I'm working in EasyCom laboratory, which is a joint laboratory between CNAM and also CNRS. CNRS is French, it's like French agency of research. If I understand, it's like BRIN here in Indonesia. So my talk today concerns the advances in physics simulation and modeling, and specifically using finite difference time domain method and the application of this simulation in advances modeling. So the outline of my presentation is as follows. I will start with the definition or give the principle of the modeling with finite difference time domain method. So once the application concerns the quantum cascade laser and the interaction of light and matter in these devices. So I will give brief description of such devices. And so the developed numerical modeling to determine or to have this quantum cascade laser dynamics, and specifically how to adapt or to use this Fdtd method to analyze the dynamics will be given in the third part. And the application is the active Modlocking of mid-infrared quantum cascade laser. Why active Modlocking? Because we went to generate short pulses for different applications like sensing, for example. And for such application, we need to have high power and large spectrum. And this is possible with short pulses. So I will give description of the method to determine this this type of dynamics in active Modlocking. So first of all, with the introduction to Fdtd method. So Fdtd method is one of computational for electromagnetics. So why you want to use this type of methods in this domain is to predict with high accuracy a large variety of electromagnetic problems. It can be like, for example, to have precise design of antennas, to for the transmission of signals in 5G applications, for example, and also for smartphones. So we know that our mobile, different mobiles have a lot of antennas with different frequency. And so now this design is complex, and with this type of computational electromagnetic methods, so we can design with high accuracy this antennas. So we have other also for other applications for defense, and also different type of microwave devices. Regarding photonics, so it is really necessary to have these tools for photonics, because now all devices are have reduced sizes, and once we have these reduced sizes, we can have large density of different devices, and we can have also on-chip integration, and so the complexity is really high. So that's why this type of tools is interesting, is really interesting in such applications. So as an example here, this is a ring resonator, for example, which is used as, for example, for sensing applications. So this type of modeling can determine what is the interaction between the light and these different molecules, for example, throughout this optical waveguide. So optical waveguides is used here to propagate light from one point to another point. And how we can design this regarding, for example, attenuation, losses, dispersion. Such tools are important to have this different kind of parameters. So this is here, and I don't know if the quality is good or no. This is an example here for how a pulse, here it's a pulse, optical pulse, propagate inside an optical waveguide, and here is the ring resonator. So we can see the different interaction, and so from the beginning we had losses, and so this we can optimize this different configuration depending on different materials, for example. This computational electromagnetic can be classified into two categories. The first one is differential equation methods, and the second one is integral equations method. So the difference between these two methods are based, or both of this method are based on the application of Maxwell equations. So Maxwell equations can be in differential term or integral term. So depending on what solution we use, both of this solution are possible. And both of these two methods need to have an appropriate boundary condition associated to the problem. So the methods provide approximations. So because we know that to use this differential equations and to use computational computers, for example, so we need to provide approximations. So we have, for the first method, or for differential equations, we use the finite differences, and for integral equations we use the finite sum. So the presentation today is with the first method, which is finite differences for differential equations. So the question is, the numerical analysis, is it possible in frequency domain or in time domain, or both of them, or which one we can use? So frequency domain is very simple, because we can have, or we can obtain analytic solutions for canonical problems. So we know, for example, as Maxwell equations, we have time derivative term, and once we analyze electromagnetic signals, and electromagnetic signals is sine wave, and sine wave can be represented in complex term in exponential GWT. So the derivative term is simple. So we can only have this time harmonic behavior to resolve the problem. So the time derivative term, which is directly equal to GW, and so it's simple to So to obtain these analytic solutions. In time domain, the differential equations are easier to formulate in time of computation. Simple to adapt in computer simulation without complex mathematics. So we can, yeah, I can explain, or I'm going to explain how it's possible. And also regarding to physical insight, time domain provide more physical precision. So because we have these real interactions between signal in time domain and the physical parameters of the problem. So in time domain, one of the or the popular method for solving Maxwell equation, sorry, for various applications is the finite difference time domain method. Now regarding this Fdtd, to be simple, Fdtd method, basic equations. So we can start from Maxwell time domain equations. So we know that we have this 4 equations. We have the curl of electric field, which is equal to derivative term of the magnetic field. This is known by Maxwell-Faraday equation. The second one is the Maxwell-Ampere equation, and the curl of magnetic field, which is given here by the derivative term in time of the component D, and D is the displacement vector, which is related to electric field. And if the medium we have losses or conductivity, so we add here the current density. And this is the convergence of the electric field and magnetic field. So hope that this Maxwell equations are familiar for you to follow easier. So the different other elements, depending on the medium, if the medium is linear, isotropic, and non-dispersive, so we can have here this vector displacement, which is proportional to the electric field throughout the permittivity, the magnetic flow, which is proportional to magnetic field throughout the permeability, and the current density, which is proportional to the electric field throughout the conductivity. So this is the general equation of Maxwell. And how now we are Fdtd equations for Maxwell equations. So only curl equations are considered. So because the differential equations can be satisfied directly from the updating Fdtd previous equations. In this case, only Faraday Maxwell equations and Ampere Maxwell equations, which are considered. And what we want is to determine the solution of electrical field and magnetic field regarding the physical problem. So here, each vector can be decomposed into 3 scalar equations for the 3-dimensional space. So we know that we can have 3 coordinate system, but yes, in the simple one, which is Cartesian coordinate, the curl of electrical field can be determined or can be computed, and so we can determine the time derivative term of different component of magnetic field as function of this the component, this spatial component of electric field. This is general relation here for the magnetic field, and we have the same thing for the electric field. Once we can relate here time derivative component of electrical field as function of spatial derivative terms of a magnetic field. So if the conductivity, or we have a medium like dielectric medium without losses, so we can directly here put sigma, which is equal to 0, and we can solve this system of equations. Then once we have this general equations here, so we can use Fdtd. These two systems here are only Maxwell equations. So now we use Fdtd to determine solution. But this one here is this one here, or this equation systems here are continued. So for any problem, we want to divide this spatial, or this geometry problem in spatial grids. In these grids, we determined electric and magnetic field components at certain discrete position in space. So because we cannot use directly this continue field. So once we use this computational electromagnetics tools, so we have to have this discrete position in space and also in time. Maxwell's equations are also solved in time at discrete time instance. And so this can be implemented by the following steps. First, approximating the time and space derivative by finite difference. So finite difference is to replace this differential derivative by finite differences. I will explain how. So next, this is the first step. The second step, or the next one, is to construct a set of equations that we can calculate the different value of fields at future time or at different time instance from the values of field at the past time. It means that it's like we increment time and we determine different component at different times, knowing the previous component. It's like sequence in time domain, and also it's like sequence also in space domain. And how we can do it with a specific time machine algorithm that simulate the progression of the fields in time. And the algorithm is known as Yi algorithm, which was proposed by Lee in 1966. Now, what is this approximation of derivatives term of electric field and magnetic field by finite differences? Here, in general case, we have a continuous function can be sampled at discrete point. So discrete point, it's like a signal that we sample the signal. It's like analog to digital converter. So we can determine only, or can select only few points to have this signal. A discrete function, so the function which was sampled is a good approximations following conditions. If the sampling rate is sufficient, it's like so in communication it's like Shannon condition, but so here we are in physics. So the sampling rate it's important. The number of points which is choose to represent the function, and also the variation of function is followed the real function, and this determines the accuracy of the method. So we cannot choose arbitrarily these parameters because the accuracy depends on this choice, and so the method can diverge if these parameters are not well chosen. Another parameter to determine the accuracy is the choice of discrete operator. So we can have different way of performing an operation on discrete function, and I will give only simple one. Yeah, this derivative operation. So as you know, if you have here, this is the arbitrary function, and which is sampled. So we have this point at x minus delta x at x point and x plus delta x. So the sampling step is delta x, and x here is the variable. So how we can determine the derivative expression of the function fx? So mathematical function is given by the following representation or following formula. The derivative term is the limit once this step go to zero or approach zero of two different points. This is the slope. That is definition of slope of the frequency. And the derivative term of frequency of a function is the slope of the function. So we can choose the derivative term at this point here, which is equal to the difference between these two values of the function divided by the step. So as the spatial step is non-zero fixed number, so we want to have this discrete point. In this case, the derivative term can be approximated to this formula, so which is equal to the difference between this point and this point divided by the step. And this equation is called the backward difference formula because we use the backward point. So we know this point, and so we use the previous point. So we can use the forward yeah, this is a mistake here. Forward. We can use another point, which is this point, and we can determine also the slope of the function. So the derivative term of the function, which is given by the difference between this point and this point value divided by the step, and this called forward, not backward. Sorry. We can use also another approximations. So where here we can use this point and this point to determine the slope here, and the derivative term of this function, which is equal the difference between the value divided now by 2 times the spatial step, and this is known as central difference formula. So what we can notice that the depending on which method we used, we can have here the difference in the slope, approximated slope, and the real slope of the function. So we can notice here the difference between this and this, and also between this real slope and this approximated slope. So the three different schemes yield to different values for the initial function, and we have the residual error, and we can estimate this residual error as, for example, by using the Taylor series approach. So in general way, this Taylor series it can be developed a function around knowing the previous point. So here the function at a point x plus delta x, which is equal to the function plus delta x, the derivative term, plus delta x squared over 2, second derivative, and so on. So after arrangement, we can determine the derivative term, which is this difference here, which is slope, minus here a constant, which is equal to the step, spatial step of the second derivative term. So in this case, we can determine for forward difference what is the O of the function, which is the error. And the error here is proportional to the chosen step, the spatial step. And here we can say that this method has a first order or is first order accurate. So for the forward method, so we can develop the same thing. We can determine what is the previous point, and the difference between the backward method is the sign here. So for this method, the sign is minus, and here the sign, the sign here is minus, and here is also minus. For the second order. And also for this method here, we have which is proportional to delta x, and this is the error, and also this method is this method is first order. As for central difference, we can use the two developed equations, backward and forward, and by here applying the difference between these two methods, we can determine the derivative term here, but the derivative term regarding the error here, which is proportional to delta x over 3, but after arranging here the O term here, which is proportional to delta x squared. So the accuracy of this method is better because here we have second order accurate method. So depending on different methods, so we can have better accuracy, and especially for this central difference, which is the first method used in the Yi algorithm. So now we will interested in this Yi algorithm, which algorithm was proposed in 1966, and the first algorithm you use this second order central difference. So what is the different steps of this algorithm? Is to replace all derivatives term in Ampere's and Faraday's laws with finite differences. In this case, with the second order central differences. And after that, we discretize space and time. But we cannot determine at the same time and the same space location the electric field and the magnetic field. So in this algorithm, these two fields are staggered in both space and time, which means that we have a difference in space and time, not at the same moment, but we have a shift to determine the magnetic and electrical field. Otherwise, we cannot have solutions if we want to determine both of these parameters at the same time. So the electric and magnetic fields cannot be described at the same time. One field is used to advance the other. So we have this this delay in time domain and also a delay in space in space. And after that, the other field will be used to advance the other and so on. And this method is known as a leapfrog method. So we determine one component, and after that, we determine the next one. This is the notion of past values or past component and the future component. So we use past components to determine the future components. And to solve this, the resulting difference equations, we employ this second order central differences to update equations. So to have this future fields as function of these past fields. But if we use the second order central difference, the implementation is a little bit difficult because we need to use another algorithm, because in the second order difference, so go back. So we want to determine the value, we want to determine the value of the next component. So how we can do it with different numerical method like predictor error method or range quota method. So it isn't simple to use this second order central difference. That's why I will only discuss first order components. So after determine the electric field, we determine the magnetic field also at different time step to have this future component as function of past component and so on. And we repeat the previous two steps until the duration in time. So if you want, depending on the time duration, not spatial, we define the time duration, and spatial dimension is derived from the time dimension. So yeah, I will explain here. I will give example for this explicit procedure. So it means that the previous, so the future component is determined from the previous component. So this is the algorithm here. We have the initial steps to have this discretized or discretized space. And to come out the different field coefficients, I will give the example. And to calculate first the magnetic field at a given component, and after that to determine the electrical field at also a given time locations. Apply boundary conditions if the physical geometry contain different materials. So we have the Fresnel, so the Fresnel coefficient to compute, and we increment in time domain. So this is how it works. We have at given time domain, we compute all spatial points, and we increment time domain to compute all spatial time. Don't worry, I will give here, I will explain better with the following steps. So from this, here I delete the conductivity to be simple. So we have this Maxwell Faraday equation and Maxwell Ampere equations. We have this derivative term, Don't worry, I only use the simple configuration. So the simple configuration, it's 1D configuration, and I choose here for the electric field a component following z-axis, and for the magnetic field, the component following x-axis. So as you know, electromagnetic wave is electric field and magnetic field, which are perpendicular components here. So the electric field is following this direction, following z, and the magnetic field is following x here, and the direction of propagation is following y axis. So from this, the curve, once we replace here the different components, knowing that Ex equals 0, Ey equals 0, and the same thing for magnetic components, so we can obtain these two equations. So the derivative term in time of electric component following z, which is equal to spatial derivative of magnetic field following x. So now these two equations are discretized in space and in time. So at time location here, the time axis. So if I can use this word, is discretized by a step delta t, and we can have n point. In the space locations, we have the same thing, and we use here the the spatial step is delta y, because this is the axis of propagation, and we have m point. So we increment m from 1 to infinite, or to, not to infinite, or to this, depending on the dimension of the geometry. As for the magnetic field, so we have this shift or delay by half, by 1, because we cannot determine the magnetic field and the electrical field at the same time. And the same thing here in space locations, we have this this shift by also half. And each point of electric field are determined at multiple of delta t and the multiple of delta y in space. And here we have this this shift for time and space. So in time, in this case, the discrete, how we can use this derivative term of electric field. So here, I omit to use this z for simplifications. It means here it's the electrical field following z, but here it's only simplification. So this derivative term, I use the backward or the this is the or this is the forward method. So the derivative term here of E, which is equal to the difference between two consecutive points in time domain. So just here, n is for time and m is for space, which means here for electric field in time domain, we have difference divided by the step. The step is delta t. And regarding the magnetic field here, which is also the difference between two successive points divided by delta t. So, but the difference is this not at the same time locations, and not also at the same space location. Here for the space, the derivative term, because here we have time derivative of electric field, and here for this we have space derivative or electrical field. And this space derivative component of electrical field, which is also determined from two successive points divided by delta y, and for magnetic field here, which is also this difference, because this what we used here, this is backward difference divided by delta y. So now I give an example here to determine as function of time. So how Fdtd work. So we have this time axis, and for a given time point or time location, we determine the different spatial component. So now we are in this point. Choose, yeah, this is arbitrary point. This is the future component, and this one are the past component, which means that all the terms here are known. The electric field at time n is known at different space location. So now we want to determine the magnetic field. So for example, we want to determine the magnetic field at this point. So we use the Maxwell Equation. So we can determine here, we have the relation between the magnetic field as function of electrical field. So at this point, we have here coordinate n plus 1/2 in time domain, and in space it's n plus half. So from this here, to determine this point, we use the previous or the past component of electrical field, because we don't know the future component. We determine the magnetic field at this time from the previous or the past component of here. The equations give only the derivative term of electrical fields. So how we determine this? So knowing that we don't have the component at this time, so we use the previous time, because this is like increment. Yeah, this value at this point, which is calculated at the previous instance, or at it's like the same instance of we have this this delay to compute different parameters. And this derivative functions is directly we use the difference or the slope, knowing this knowing the value of this component and the value of this component in space locations, so we can determine after that the component. And so this one is discretized. This component is determined from the previous one, because this one is known, is past component, and so on. And then we can determine or write this component from the previous one, from this one here at the past location time, and as function of this two component of electric field. Yeah, we have this constant parameters in the algorithm of Yi algorithm. So the initial parameters is the computation of this, because this this coefficient is the same for different steps. So regarding Maxwell-Faraday equation, so we have this derivative term of electric field in time domain as function of derivative term in spatial for the magnetic field in spatial domain. So as an example, we want to determine this point. Here, this dashed line is the frontier of the separated just separation between the future and the past. So the past here, all these elements, it means that the magnetic field at time n plus half at different space location the magnetic field components are known, and also this previous electrical field are known, and we want to determine the different or the new component. So, for example, for this one, this component is determined from the previous one due to this derivative function, and depending also on this spatial derivative of magnetic field. So from this 3 parameters, we can determine the next one, and so on. So once we determine the electric field, we can determine the magnetic field until so the final time, because once here the final time is known, the start time is known, and the final time is known. Yeah, this is here the electric field and the new component of electric field, which is equal or is computed from the previous field in the same space. This is the same space location, but not at the same time, and also at the same time for magnetic field, but not at the same space location. And this one here is the constant value. So with this is the initial parameters of the program. This is only simple. This is 1D computation. It looks like 2D because we have time and we have space. Yeah, but we have a more complex configuration, which is 3D. So I don't explain this because it's a little bit complex. Now, once we have this finite difference, so how we compute the different electric and magnetic fields. So I can now give an application for this for quantum cascade laser. But before I will give little description of quantum cascade laser. So knowing in the semiconductor lasers, so once we have here electron transitions from conduction band to valence band, so we have this radiative emission. It means that photons are generated once the electrons move from conduction band to valence band. And the wavelength of photons are given by the gap energy, the difference energy between this conduction band and valence band. However, in quantum cascade laser, we use other technique to have this radiative transition. So, and we use this inter-subband transition. It means that inside conduction band, we can process or we can realize different or sub-conduction bands. And the transition of the electron from one subband to another can be radiative, and the wavelength is determined by the difference, and this is given by the material engineering. And I will give an example here how we can do this. So semiconductor, we know that in semiconductor we have energy of the gap, which is the difference between conduction band and valence band. So in quantum cascade laser, we can here have these different wave equations, because we know that electron is a particle and wave at the same time. So we have here a condition for wave functions depending on the system. Here is the succession of different materials. The materials are the gallium arsenide and aluminum gallium arsenide material. And the number here are the width of these materials. It means that here we have 5.8 nanometer of gallium arsenide. And the next one is the Al gallium arsenide with the width 1.5. And so on. We have 2 nanometer, 4.9 nanometer, 1.7 nanometer, and so on. Here is the difference energy between gallium arsenide and gallium arsenide. This is depending on the gap energy difference between these two materials, and also regarding to work function. So we can have this vacuum energy as a reference between these two materials, and this is a gap, and this is the difference energy between these two materials that we can here determine these functions. So we'll try maybe to give here an example. I don't know if we share a good thing. So how this is typical one. Well, this is the energy, and we can determine the function or the wave function solution inside this this energy well from or using Schrödinger equation. So we can determine the wave function, and here this is the probability of density, and this is the function. The function is like here half of sine, and this is a solution for this one. So if we modify the width, so we can have another solutions like here, which is because in this quantum well we have the standing wave, and the standing wave we have here probability of existence of electron at a given energy, because energy is quantized inside this quantum well, and so we can determine this with or using Schrödinger equations. So if we have multi-wells, so in this case we can have this different state functions. So for example, here I don't know how number we have five wells here, and this is a difference energy. It's like in the quantum cascade laser. This difference energy is between two materials because you use two materials. Here is computation, but so we can understand or we can have this comparison between quantum well and this theoretical computation. So here we have this wave function, which is here in yellow color, and also the different wave function possible. And we can determine the transition or the difference energy between this energy E6 and this energy E5, and this one can give the wavelength of photons. And in quantum cascade laser, that's what we can realize here, that it's different functions as function of the width and the material here type and the thickness of each material here. Yeah, how we calculate this? This is, for example, a paper to modeling techniques for quantum cascade lasers, and we use the Schrödinger equation to determine the wave functions of different width or thickness here of materials. We can the thickness here, the width of the materials are very important, and so here the scale or the unit here is nanometer. Regarding the materials, we can use different kind of materials. We can have here gallium arsenide substrate, and we can, for gallium arsenide substrate, we can have this both materials. For example, here we can know the difference of energy between gallium arsenide and this aluminium gallium arsenide, and so on. So if we use this one here, ENA's LSB, so we can see that the difference energy is very high, which is 2.1 electron volt, and this gives the possibility to have the wavelength. For example, with this materials, we can have wavelength around 2.6, and the other from 3 to 5 micrometer, and on gallium arsenide substrate from 8 to 12 micrometer. And quantum cascade laser is built. So this one is the radiative region, which is composed of multiple layer of two materials with different thickness. And quantum cascade laser is the cascade of this active region, for which one electron can generate multiple photons, because here the electrons who is injected in the top of the active region, here once we have here radiative recombination or radiative transition. So this electron generate photons, and the same electron here go to the next active region to generate second photon, and so on. And this is the principle of this quantum cascade laser. So an example here, this is the active region, and the active region, this one is the injector, a radiative shear region, and we have this multiple succession or multiple cascade of active region, injector, active region, injector, sometimes or in general case between 20 to 50 times this region. So what is important here thing is to have this radiative emission between these two states, and after that we have different type to have this electron. This is here how we inject the electron to the next one. Here is the tunnel effect. We can use phonon or double phonon, and we have different type of this is depopulation. Yeah, this is a picture of the device. So the active region, this here multipliers is in red color here. So to have, we should to bias, we inject a current, and once we inject current, so yeah, why we have this type, this is oblique region. So it's, we consider here that this active region is biased. So once we bias the active region, so the last level here, which is at the same level of energy of the next one, and so on. It means that the last level here, which is at the same level energy of the higher state for the next one, and this built once we have threshold current. When we have threshold current, so we can have this current or electron displacement inside this active region. So the electron move from the top. So when we bias from the top and collect it here at the bottom, and the photon, once the photon is generated, so we have this longitudinal mode or the propagation. The photon propagate in longitudinal direction, and the electron go from the top to down. Here, an example of the generated spectrum at 4.7 micrometer. So the devices are as following. So the active region is here. The active region here, I don't remember exactly, it's between 30 and 35 active region. And we have here INP material and the INP material down, and only here the active region is here, and this is the same in the red, in this red region here. So once we apply a current after the threshold value, here the threshold value is 220 milliamp. So we have here the wavelength or wave number. We have here the generation of single mode wavelength, which means we have only one wavelength. But next, I don't have time, but for the next step, for the Modlocking, we want to have this multi-mode operation. So here, once multi-mode operation, once we increase the current, so we can see here in the spectrum that we have multiple wavelengths generation, and this is called a multi-mode QCL or multi-mode spectrum. It means that the gain it's very broad compared to this one. So here the gain is really very short, spectrum gain is very short, but once we increase the current, so we can increase the gain spectrum, and we can have this different wavelengths. Yeah, now how we can model the QCL dynamics. What means the QCL dynamics? It's the what is the relation between electrons here, injection, when we inject the electron, and the relation of photons. So that is what we want to understand with this QCL dynamics. To understand or to have this idea about the QCL dynamics, we are interested in the interaction between light and matter. So we have different kind of formulation. For example, we have a dynamic. This is we have two techniques to determine this. Either rate equations. Rate equations means that we can determine the time evolution of electrons, for example, and time evolution of photons, and we can determine what is the relation between electron and photons. This is a rate equation. Otherwise, when we have here ultra-fast pulse, and so interaction of ultra-fast pulse with matter and with high power, so it's better to analyze with another tools. And here, I will give here description about this two-level atom approximation. So two-level atom approximation. Why we use this? Because regarding the different energy levels or wave functions in the quantum cascade lasers, so the emission is between the high level and the second one. So here, for example, once we have this is for depopulation. The dynamic is or the interesting dynamic is between level EB and level EA. So here it's like two atoms level, and that's why we can use this approximation to determine this interaction between QCL and light. So the difference between the energy here, EB and EA, which is equal to the photon energy, and the photon energy here is related to the wavelength, and this gives the wavelength. This laser dynamic, can be described by Maxwell block equations. Now, here just brief description of block equations. Yeah, block equations, it's like a mean description of the different states. I don't know why we have this. It's like, yeah, mean value of different states. So we have here the time evolution of the density matrix, which is given by the following relation here: the time variation of density matrix, which is given by the commutator of Hamiltonian and density operator. So we have here a matrix with 4 components, and we can determine these 4 components to analyze here the block equations. Yeah, this diagonal components are the population. It means that here this derivative term means what is the population variation in this ground state, and the term here describes the population variation in this excited state. And the anti-diagonal elements are the coherences. And the coherences means that what is if you have your electron at a given wave function, what is the phase difference once the electrons go to this ground state? And this is the difference or the phase or relative phase difference between these 2 states. Maxwell block equations concern is to determine these different parameters. As for Hamiltonian operator, we have Hamiltonian here without light interaction, and the Hamiltonian here with light interaction. So without light interactions, it's only here the diagonal term, and the Hamiltonian with light interaction, which is proportional to this electric field of light times the dipole moment. So after that, we can determine the variation of density matrix from the commutator between Hamiltonian and matrix density operator to have this different matrix element. This is the population at crowd state, population at excited state. This is the coherence, and this is the coherence, knowing that the coherence rho AB and rho BA are complex conjugate. So we can relate this. This with interaction with light, so we can determine the different parameters to understand or to have this population evolution and coherence evolution in time. So, but as these parameters are complex, so it's better to use real parameters. We introduce here we introduce here a value or parameter rho A, which is the sum of rho AB and rho BA, and this one is probability of electron existence in the ground state. This is the probability of excited state, and we determine here the population inversion. The population inversion, so we know that it's important to have this laser emission. So laser emission, the population in excited state should be higher than population in ground state. So that's why with this parameter, it's better to understand the dynamic, and it's easier to implement contrary to these complex parameters. Maxwell equation, we know the equation. So keeping with the 1D configuration, we have also almost the same thing here. The electric field is following Z, magnetic field is following X, and direction following Y. So the difference with the previous one is this term, which is this term is the polarization, because we have this polarization effect. And in quantum mechanical description, we can relate this polarization vector as function of the anti-diagonal element of density matrix. So after that, we have this Maxwell block equations, which give the relation or the time derivative of magnetic field as function of spatial derivative of electric field, and also time derivative of electric field as function of magnetic field, and also as function of polarization vector. And this polarization vector depend on the probability of existence of electron in each state and the carrier inversion. So we can add also here nonlinear term in the this electric field, which is losses, and this one is nonlinear losses like saturable observer. And we can add here also diffusion. Diffusion means that we have leakage of carrier as function of space. So sorry, here it's Y, not C. Yeah, now once we have this Maxwell block equations, we can determine, or we can have or resolve the solution using different methods. And so it's simple to use directly Fdtd because we have here configuration type domain and spatial domain. Otherwise, we can use simple, other numerical method. So the question now, to have this sample description or complex expression, complex description, an example is for this equation here. So this one is the probability. So, to determine rho A or to determine rho B, we know we have here to determine to know electric field. But electrical field depends also on this parameter rho B. So it's difficult to compute one and to compute the other one. So that's why we have two possibilities. Either to choose the time sampling or time locations at the same time of electric field to determine this rho and this population conversion. Otherwise, this is known strong coupling. Otherwise, we can choose to compute this block equations with the same time as the magnetic field, and this known weak coupling. So, but the accurate method is this one, but with suitable conditions. So we can use this, and if you use this this one, the implementation is simple. With this one, the implementation is complex. We need to use another type of numerical computation, like predictor error, for example. So finally, once we apply Fdtd method, so we can determine here the magnetic field, electric field, and also the probability of existence of electron at ground A, at state B, and the population difference. So this is here mathematical description, and this is here Fdtd implementation. So after that, we can implement this using programming language to determine the solution. As an example, we have this this configuration. We have quantum cascade laser, and we have only quantum cascade laser here. This is a vacuum to simulate a realistic configuration. So because, as I showed before, so we have this quantum cascade laser when the light is directly emitted from the facet of laser to the vacuum. And so after we can here analyze the evolution of this is electric field, and in red color here is population inversion. Yeah, this one is delta, and this one here is electric field. So the configuration here is the we use the secant hyperbolic field here as condition initial. At this position, we inject an electrical field with a given amplitude, and we show here the propagation of electrical field, and just here the initial condition of the population inversion, which is equal to 1, which means that the QCL is fully inverted, and once the electrical field propagate, we have here the total inversion. This one, it's like stimulated emission. This is known p-pulse, and for 2 p-pulse, it's like SIT, which is self-induced transparency, so that we have the initial population, which is non-inverted, and once the electric field propagate inside the medium, so we have here the total inversion because the light is absorbed, and after that, the population are completely inverted, and so it's like propagation without any loss. This is called SIT, and so we need a specific amplitude. That's why the amplitude here of the electric field is calculated to determine this effect. So the last point here concerns the active Modlocking. So Modlocking here is used, for example, to obtain short pulses. So we know that in this cavity, laser cavity, you can have a lot of photons with different energy, which means that we have different frequencies. So once we have here a random phase of this longitudinal modes, this is Fabry-Perot mode. It means that we have the standing wave. If the phase are random, so the sum of these different states of different modes, so give either CW state, a continuous state, or here we don't have or the laser here operation files. But once we have in time, we can produce this, sorry. So if at a given time, we have all the phase of the different modes are the same or in phase, so in this case, we can, at this time, we can have this pulse generation. And so the width or the duration of pulse depends on the number of modes, and also the power or depend also on the number of modes. So regarding the spectrum in the frequency domain, so this is the single one. We have only one frequency. We have no spectrum. This is only CW mode. CW mode means we have only the only wavelength. But if you have this multi-mode, that's what I shown from the measurement few slides ago. So if you have this number of mode which is high, so we can here have a generation of short pulse, and the duration depend on the size, or the duration depend on the width of this gain spectrum, and the power depend also of the number. Here's an example of the mathematical expression of this pulse, and this W0 is the with the frequency of the optical signal here, the center frequency. And this is here the envelope of the signal given by this term here. What is Modlocking technique? Active Modlocking technique. Sorry, here is the passive. So the passive is I changed it because it's simple. This active Modlocking. So Modlocking, we need to have the same phase of different modes. So in this case, inside the cavity, we add the modulator, which is an electro-optic modulator, for example. We can use acousto-optic modulator, and we applied an external radio frequency signal with the frequency which is equal to 1 round trip time. So in this round trip time, they depend on the length of the cavity. What's happened here, once we do this, we can modulate the loss of the modulator. And so we have the gain conditions or the laser conditions. Once we have the gain which is higher than the loss, we can realize this laser conditions. And so once here we modulate the loss of this short section modulator, so we can generate multiple pulse. So now I use the previous configuration. We only here inside the short section, we apply radio frequency signal, and this radio frequency signal depend on the length of the cavity laser. The cavity is the total cavity here, which is DC to have this the threshold condition. And in this section, we have RF and DC. We apply this RF signal in order to have the same phase, to trigger all phases of different modes at the same frequency, at the same phase. So,
Salim, you have 5 minutes.
Yeah. This is the, we have two slides. Yeah. So what is the difference here? What is the difference between this short section and the previous one? The previous one is the same equation as the previous description. So in this short section, the only modification is this injection current, and also we add nonlinear parameter, which is here the diffusion term. And so we have this implementation, so we can show that without RF signal, we don't have the generation of pulse. So this is the blue one. So without RF signal. And once we apply RF signal, we have the generation of this pulse. The difference here is the round trip time. And the zoom of one here, this is the generated pulse. Once we apply here a current which is equal to 1.1 the threshold current, and for a given here parameters. That's all. Maybe a little bit long. I don't know.
Yeah, it's okay.
Thank you.
But it was very interesting, and I think many of us like the way you present, because it was so slow and also educative. And alhamdulillah, I think hopefully that many can follow your lecture. It was a very interesting lecture, because you start from the discretization, and you explain how to the algorithm of the discretization. So and use this analogy, also this method for the quantum system. In this case, the quantum cascade laser. Yeah, and so the students here, after watching your presentation, hopefully can at least appreciate the application of quantum mechanics. That if you have narrowly confined system, you have to use the quantum equation or the Schrödinger equation. And starting from the simple potential well, which you will study in the quantum lectures, you can have multiple wells, and with the combination of like heterostructure material like gallium arsenide, and with the electric potential, you can have a cascade energy. You have this kind of intra subband transition. So the subband transition is the key to this cascade laser application. And here the student can see that you can downgrade the energy from visible into lower than 2 electron volts. So it's the mid-infrared. So for the student, it's very interesting that you can manipulate the outcome of the laser light using quantum mechanical principles. And what is also interesting is you can simulate it, not only experimental, but also theoretical using the finite difference method. And this is very good presentation, and I thank you once again. So let's give first an applause for Prof. Salim for his presentation.
Thank you.
And now let's go to the question session. We have lots of people here in this room, hopefully future physicists, future physicists.
Yes.
And now the opportunity, I would like to invite you to ask a question to Prof. Salim. And I will maybe give the opportunity also to introduce the PhD student, maybe Mr. Teguh. Mr. Teguh, you can turn on the camera.
Okay, I will try to see.
Yeah, Mr. Teguh.
Okay.
Yes.
Mr. Teguh.
Yes.
Mr. Teguh is also a collaborator with me in Prof. Alatas, and Mr. Teguh also study finite difference methods. In particular, also dimatiin aja dulu. He can also use the finite difference frequency domain technique. And it would be a great opportunity to meet Prof. Salim Teguh. Is that correct? Hello? Yeah, maybe he is still we
were in the same situation yesterday, so I understand.
Yes. So hopefully he can follow your topic and also present his idea to you regarding the topic. Probably also he can do the FD simulation of cascade laser. That would be interesting, right? FD for the cascade laser.
Yeah, sure. We can have a common project together.
Yeah, because as far as I know, your simulation is still limited to finite difference time domain, right?
Yeah.
And Mr. Teguh, he has experience in frequency domain. So in frequency domain, he can try to find the interband energy if using FD.
Okay.
Yeah, and maybe this can be one of the collaboration topic. Is
FD to determine the energy levels in this quantum wells.
Yes, and also the possibility to expand into 3D, even though it's difficult. But I think there are many open possibilities. Okay, so for the forum, forum, any questions? Maybe from Pak Tony.
Oh yeah, thank you very much. Yeah, it's really interesting and nice presentation from Professor Salim. I just wanna, it's not like a question, but just maybe correct me if I'm wrong, my understanding. When you talk about the quantum cascade laser, the example that you bring was aluminum gallium arsenide and gallium arsenide structure, right?
Yeah.
Yeah, actually, I did before the inverted structure, the gallium arsenide and aluminum gallium arsenide. I did before the inverted structure, the aluminum gallium arsenide and gallium arsenide, but my simulation was for multi-junction solar cell or dual junction solar cell. So if I see the difference, so is it true that the difference in philosophy here in dual junction solar cell, we try to maximize the absorption, but in the quantum cascade laser, you invert the structure in order to maximize the emission. Is that true?
Yes.
Okay. Yeah.
What you want to do here is to realize these different wave functions and to have here a good energy difference for a given wavelength, because the wavelength here is determined between the by the difference between the levels, so such type of substrate, gallium arsenide, anionic arsenide materials, is to build or to have a given wavelength, because so as I put here, so we have in general two type of technology, either on gallium arsenide or on ENP. And depending on the material choice, it's easier to realize or to have this wavelength range here on gallium arsenide. Otherwise, in the from 3 to 5 micrometer on INP. But sure, what it is desired here is to have this
mission.
To have this different synergy between two levels, and those one are radiative energy.
Okay, maybe I can also add something, Prof. Salim, and if I'm wrong, please correct. So in Patoni's case, I think you analyze the bulk structure, because in this bulk structure you have always this conduction and valence band and conduction band. So you produce this kind of electronic transition, exciton transition, but in the quantum cascade is very thin. So because of the very thin, this is more related with the intra subband transition, not the exciton, but the intra subband, because it's very thin, and therefore you have this cascade structure. I don't know if this is also a relevant answer to the question, that because in the normal case you have the bulk structure, and in this case you have a very thin structure, so the emission is more concerned with the emission, right? Because otherwise you have this exciton state, right?
Yeah, you're right.
Both are thin film, actually. Yeah, in dual junction solar cell and also in quantum cascade laser. The difference is the one try to maximize the absorption in a dual junction solar cell. So, but in this case, in laser, you try to produce the radiative, right? You try to produce the emission. That's why you invert. In a dual junction solar cell, the top layer is the highest band gap, and the bottom layer is the lower band gap. But in this case, you invert, right? Because you're trying to get the emission, the radiation,
so the population inversion. The population inversion.
Sure. But if I understand, the dual junction, it's like pin diode, which is with different materials.
Yes.
Yeah. But you have in the same, in the bulk material with valence band and conduction band. But the absorption depends on the gap energy, and not here depend on the electron states. In quantum cascade laser, what is the difference between bulk material is to have these different states inside a conduction band, to have this electron conduction because the
Lost connection, I think. Yeah, I think that's enough from me. Thank you very much, Salim and Pak Dodi. Maybe other participant can also ask the question.
Okay. Okay. So for the students, come on, students. It's okay if you can ask anything, yeah, related to this topic. If you want to study quantum mechanics, I think you should after you study it, you can understand at least the basics of this device. Maybe Prof. Alatas, you want to give comments?
Yeah, I have one question, Prof. Salim.
Yeah.
When solving the Maxwell block equation, what kind of boundary you use? Is it also PML? The perfectly matched layer when solving the Maxwell block equation?
Yeah, about the condition limit. Yeah, I didn't speak here about the condition limit.
Yeah.
Yeah, because not simple to use this. We used 3 layers, absorbing layer. With
Absorbing layers.
Yeah.
The PMLs.
Sorry?
The perfectly matched layer.
Yeah, perfectly matched layer with 3. I think with 3 successive layer. Okay. So we can use different type of absorbing layer. This is ABC. This is here the limit absorption layer boundary condition. So for student here, so when we simulate such type of structure, so we have the light, the propagation of the light here in the longitudinal section.
Yeah. Freezing.
Perhaps connection is problem in in Salim's place, the Prof. Salim place. Okay.
Is it okay now?
Yeah. Okay.
Sorry. So I said here. So the light propagation is the following this longitudinal direction. Yeah. And now here we have the Fresnel reflection between the quantum cascade laser and the vacuum or the air. But for the simulation setup, to console any reflection at this side and also this side, we add here boundary condition, and this boundary condition is to console the reflections, and we can find different type of boundary conditions, and here we use the absorbing boundary condition.
Not the PML.
Not PML. This is absorption boundary condition.
Is it enough?
Yeah, enough.
It's enough. Okay.
Yeah.
Okay, thank you.
Okay, thank you.
Yeah.
If there is no more question, I just have one curious question regarding the modeling of cascade laser. There is still some Maxwell involved, even though it's a quantum system. Is the quantum mechanics inside the matrix density, or how do you integrate? Yeah. Okay.
Yeah. We use this this approximation, which is called this 2-level approximation. So we want to have this the evolution of light propagation inside the QCM. So knowing that each laser device generate the light, and the light propagate inside and interact with the matter, and also the matter have an interaction with light. If the light intensity is really high, you can generate also, you can have this nonlinear interaction. And so here we use this two-level atom approximation, which is described by these Maxwell block equations. So because in quantum physics, so regarding here to the state of electrons, so this is state, but you have not only one electrons, you have, so when you bias the laser, you have a lot of electrons, and you have also the interactions between these electrons. So that it's difficult to analyze this directly by directly from the I will say the Hamiltonian or Schrödinger equations. So you can look, it's like a mean value or a mean function, and this mean function is given or formalized with this block equations. So block equations, we have an introduction of this density matrix, and this the evolution of the system, it can be determined directly by the time derivative of this density matrix. So the density matrix here is defined as the commutator between the Hamiltonian and the density or density operator.
Okay. So there is already the quantum mechanics included in the equation, yeah. So
yeah.
So okay, and we apply the same technique for the discretization. So the partial differential.
What is the important thing here, which is the important thing also here is the dephasing or the coherence. The coherence here is really important because the phase at this state and the phase at this state, it's really important. And this quantum mechanics give this coherence that we cannot do it with simple rate equations, because rate equations, it's only this dynamic, but the coherence here is very important. And the quantum mechanics, the phase, we know that the states, the electron states is a complex, and the phase can also be important.
Okay, thank you, Prof. Salim. Okay, students, any questions? Yeah, so maybe because you are still confused about the quantum stuff. But...
Yes, Pak Dodi.
Yeah, please, Pak Fauzan. Yeah.
I have one question, Professor Salim.
Yeah.
I see in your slide, I see in your cascade model the electronic structure of gallium arsenide with model with a 3-level cascade system. How we can simplify the electronic structure of gallium arsenide into 3-level cascade or 2-level cascade system? How we can justify it to get this simplified?
No, we cannot with the gallium arsenide. So to have these different levels, we need to have this multiple wells. Otherwise, we cannot do it. If you use directly the bulk gallium arsenide, so we have an idea about this different bands. So we have conduction band and we have valence bands. And so in valence band, so you have heavy band and so on. But to have this multiple states, you have to, you have to realize by engineering this different states, and this is done by the multiple. So as an example is given here, or the previous one, here. So to realize this multiple states, the different states, these different states are built from the multiple quantum wells. And the depth of each quantum well is important. That's why this type of structure is done from simulation. So that's why I present this paper here. This paper here from Schrödinger equations. So you can determine different functions as function of the thickness of each well, and also the difference here. That's why you can find here, this is the quantum bound states. So here with single well and with multiple well, so you can have an idea about the different states. This is a theoretical aspect. So we have here the difference energy of the well, we have multiple well and with the difference of well. And this one can be realized. How can be realized? But this multiple well. So depending on thickness of each one. So here we can see that if we modify the difference, this is the energy here. If we modify the difference of energy, we can have different states. And this different states here is state for electron, the same thing here. So if we use different materials with the energy difference between these materials, we can see here for this ENRS ILSB. So we can see that ILSB is this one, ENS is this one, and this is the difference of band gap. So the difference of band gap give the height of this well. And so quantum mechanics through Schrödinger equation can give you what is the wave function. And so the designer of these quantum wells try to have the better, but it's complex. Not only the difference, but the injector is very important, because here once you have the radiative emission in this first active region, you should to have depopulation. So electrons should be injected to next active region. And so the time transition here should be very low. As an example, so you can have radiative emission here, the carrier or electron lifetime about 1 picosecond. But the depopulation time, so the time for electron to go from this active region, so from this point to this point, should be less than picosecond. Or otherwise, so you cannot have high efficiency. And typically with the tuning effect here, which is another quantum mechanics effect, with this tuning effect here, you can have this transition time about a few femtoseconds.
Okay,
Prof.
Salim, sorry.
Yeah,
I think we are out of time, but if you can just comment on the last question. So what's the program you use for Fdtd and the general algorithm? Yeah, I think it's the first question is just look at any Fdtd book. But the second question, what is the software you use? Thank you.
Yeah. For the software, you can use different programming software. I use C program, C script.
Oh, C program. Okay.
Yeah, but but it's possible to use with
MATLAB and some other programs.
Python.
Okay.
Python, it's possible. MATLAB and Fortran. Fortran is the old programming language, but there is not. But it's better to have an idea about these programs to. For 3D, for example, you should to use this parallel programming. And so I think if you use MATLAB, you have this facility to use this this parallel programming, because Otherwise,
Okay.
if for the homemade program, you should to do it
Okay.
by yourself.
Okay, thank you, Prof. Salim, for your excellent presentation and answers. I'm so sorry because the time is limited.
Yes,
So
yes,
we
sure.
are going to give you maybe a kind of certificate of appreciation. So if I may share the screen, please. Can you make me co-host, moderator, or yeah? Okay, so I would like to invite maybe Prof. Alatas to present the certification to Prof. Salim.
Okay.
Okay, yeah. Yeah, this is our traditions, Professor Salim.
Yeah, okay.
Yeah.
Okay, back, Hassan. Thank you.
We would like to give you a token of appreciations in the form of this certificate of appreciations. We are very grateful that you can give your presentation here right now. As Dodi mentioned, that this is the first foreign speaker in physics talk, and I hope you enjoy our discussion now, and we can collaborate further, especially in the PhD program of Mr. Teguh.
Yeah.
Yeah, and also we can make further collaborations between the Department of Physics and your department in Senam and Kenam. Yes,
Yes.
how do you spell Kenam?
Yeah, Kenam, yeah.
Kenam.
So.
Okay, thank you very much.
Yeah, thank you, Pak Hassan.
And also maybe Prof. Tony, you want to make closing remarks for our guest, and also maybe thank him for the visitation. Thank you, please.
Yeah, again, thank you very much, Prof. Salim. Yeah, it's an honor to have you several days or several weeks here in Bogor. Really inspiring and really insightful for us. And like Prof. Husin said, hopefully this will continue with the next collaboration, next work, next effort, and to increase the quality of research education, especially in IPB University. So if you have time to come again to Indonesia, please come again to Indonesia, to Bogor especially. Yeah, and again, thank you very much, and really appreciate that. Yeah, Assalamualaikum.
Waalaikumsalam. Thank you, Pak Tony.
Okay, and by the closing remarks, I would once again thank the speaker and also all the participants. And after all, we all have something in common. We love science, we love physics. So please stay motivated and get the Prof. Salim. If you have time, please come back again next year.
Yeah, inshallah.
And inshallah, Pak Tony, Pak Husin, we are welcome to have you here again. And so I close this physics talk today. Alhamdulillah. Assalamualaikum warahmatullahi wabarakatuh.
I would like before to thanks all staff in IPB for the kindly welcoming. So it was very nice weeks. I was here from 3 weeks, and I really appreciate all time past here. So thank you for different discussion and for the welcoming. And so hope next time, inshallah. So I also visit IPB. This is the beginning of we collaborate since 2 years, but so we will continue to collaborate in the future. So thank you very much. Thank you, Dr. Hindradi, for your assistance, for your help.
And maybe before you leave, just a small photo session for those who can turn on the video, please, for 1 or 2 seconds. You can turn on the video, please.
And also
Yeah.
thanks for the student and
Yeah.
for the staff, for IPB staff.
Okay, please turn on the video if you can do. Yeah. Okay. So
You should.
if you students if you want to you can study hard and you can visit France maybe, yeah, in the following years, yeah.
With this graduate program, yeah, you have a chance to follow PhD position, and so
yes, and you
it's
can
possible
visit Paris perhaps, right?
Yeah.
So
Paris and lab and to work in
France.
in
Okay.
France and so.
Okay. So
Yeah.
thank you. Okay. If not, it's actually I feel a little bit sad to close this session because
Yeah,
of course you have we have lots of memories here, but yeah, I hope that this is not the last meeting, and we can inshallah meet in the future also with all the students and all the lectures here.
yeah,
So thank you all. I close this session.
yeah. Thank
Good,
you.
yeah, good afternoon and assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Bye.
Thanks,
Bye.
Prof. Salim. Yeah.
Thank you, Pak Tony.
Yeah.
Permission to leave.
Yeah, thank you.
Oh, bye bye,
Bye.
Salim. Bye bye.